So if we call Fn the generic term of the Fibonacci sequence, then the terms are related to each other by this formula. It means that the nth term is equal to the sum of the two terms immediately preceding it. Okay, so we know that the terms of the Fibonacci sequence are 1, 1, 2, 3, 5, 8, and so on, 13, etc. Okay, so the particularity of this kind of relation is that it is an equation in which all the terms are of degree 1. You know, the degree 1, or in other words, this is a linear relation. Okay, and I should start recording. Go to the left.
Recording in progress.
Okay, so about the recordings, I forward the question to the IT department, so hopefully they will have the answer. Okay. By the way, next week we will have hopefully offline classes, so I hope that we will need recordings anymore. Okay, in the second example about the tower panel, we have this relation. This is also called a linear relation because you can see that the terms here, we have Hn equal to 2 times Hn minus 1 plus 1. So there are no quadratic terms, or there are no cubic or larger order term here. This term h1 is linear because the exponent here is 1. This one is also linear, and this is a free coefficient. So this relation is also called a linear recurrence relation. Okay, but the difference between the two relation is that here in the relation of the Fibonacci sequence, there we don't have a free term, so this relation is called homogeneous in Vietnamese. That means đồng nhất, thuần nhất. Okay, and the recurrence relation of the problem of tower of Hanoi is not homogeneous because there is a free term here. Okay, similarly, this in the third example about code words, we also have a linear and non-homogeneous recurrence relation. Okay. So in the next two parts of this lecture, we will talk about linear recurrence relation, and we will distinguish two cases. The first case involves homogeneous linear recurrence equation. Okay, so the recurrence relation of the Fibonacci sequence and of the tower panel problem was here. Take a look. Okay, so this recurrence relation, we can see that in order to calculate Fn, we need to know the two previous terms. We have to go back two indices. So this recurrence relation is set to have degree 2, because we have to go back two terms. Meanwhile, in the problem of Tower of Hanoi, we have a relation of degree 1, because we only have to go back one term in order to calculate the next term. And here in the code word problem, we also have a relation of degree 1, because in order to calculate a n, we only need to know a n minus 1. We don't need a n minus 2 or previous terms in order to calculate a n. So this relation is said to have degree 1. So in general, when we have a linear recurrence relation which is homogeneous, in the sense that here, in order to calculate, this relation is expressed as an equation whose left-hand side is an and whose right-hand side is a linear combination of the k terms preceding an. And we say that this relation has degree k if we have to go back k terms, okay? And additionally, we want that this coefficient is non-zero. It is a technicality, because if we don't impose the condition that ck is different than 0, then we can also write that we can add as many other terms at the end as we would like. So the degree would be indeterministic. Okay, so we want the degree to be unique, to be fixed. So we impose the condition that ck is non-zero. Okay, so with this condition, you know that the degree of a homogeneous linear recurrence relation is unique, is uniquely determined. Okay. So for example, for the Fibonacci sequence, we have fn is equal to f minus 1 plus f minus 2. So we can simply say that it is a homogeneous linear recurrence relation of degree 2. You can write that, you can extend it like that, but it doesn't add anything because this coefficient is still 0. Okay, we only count until the last non-zero coefficient. Okay, but note that if we have a sequence defined by a of n is equal to, for example, 2 times a n minus 2, this is also a recurrence relation of degree 2. Okay, so here all the previous, but the previous coefficient is 0. Okay, so all the previous coefficient may be 0, but the important one is the last coefficient. The last one should be non-zero if the degree of our recurrence relation is k. Okay, understand? Okay, so here homogeneous means that there are no other coefficients. So let's say that if you have a 1 here, then it is not homogeneous anymore, or as in the previous example, you have a term 10 to the power n minus 1. So if there is such terms, then the relation is no longer homogeneous. Okay, so in order for it to stay homogeneous, there must be only linear terms involving the terms of the sequence, no other terms, no no free coefficient, no coefficients, no functions of n, etc. Okay, and this in Vietnamese is called quan hệ truy hồi tuyến tính thuần nhất bậc k. Okay, so if you would like to look up the name in Vietnamese, then you can translate all these terms and do a quick search. You find documents about it online or in paper. Okay, so here in our course, we only consider real numbers. Nothing forbids the coefficients to be complex number, but for simplicity, we assume that we only work with real numbers. Okay, so all the results can be extended to complex numbers if you like, but if for this course, we are happy with dealing only with real numbers. Just keep in mind that there are no reasons to limit ourselves to real numbers. So every result that you see in this section also apply to complex number as well. Okay, so when we talk about recurrence relation, often there is only a relation like this, but in order to uniquely determine a sequence, we need some initial condition. Okay, so here, for example, if you fix the first k term of the sequence, if you fix these values, then you know that because of this relation, if these values are fixed, then the value of ak is uniquely determined. Okay, and once you know ak, the value of a k plus 1 is also uniquely determined because ak plus 1 is a function of a1 to ak, and so on. So if we have a recurrence, a linear recurrence relation such as this one, and we have k initial conditions, that means that the first k values of the sequence, then the sequence is completely determined. Okay, so there is one and only one sequence for each recurrence relation coupled with a set of initial conditions. Okay. So as we pointed out, the recurrence relation of the Fibonacci sequence is a homogeneous linear recurrence relation of degree 2. Meanwhile, the recurrence relation in the example of Hamlet Tower is linear but not homogeneous, and the degree is 1. And the recurrence in the example of code words is also linear but non-homogeneous and of degree 1. Okay. So now our goal is to, of course, you know that if given an initial condition, our sequence is uniquely determined. But if we want to have some way to calculate the the nth value of the sequence quickly, then we need to find some general formula of the sequence. Of course, if you let's say that you have the Fibonacci sequence, right? You know that you have this relation fn is the sum of fn and fn minus 1 and fn minus 2, and you know that f0 is 0, f1 this one. Here, there's another remark. So in our exercises, depending on the context, sometimes we start our sequence with the index 0, sometimes we start with 1. There is no fixed rule regarding that, okay? So sometimes you will have exercises in which your sequence are indexed by positive numbers, but in some other exercises you have sequences that are indexed by only non-negative numbers. Okay, so you may start with the term indexed by 0 or the term indexed by 1. It depends. Okay, there is no fixed rule. Is flexible. Okay, so sometimes this Fibonacci sequence, sometimes you see that the initial condition is f0 is 0 and f1 is 1. But in some other document, you may see that the initial condition is f1 equal to f2 equal to 1, but there is no big difference. Okay, so it's only a convention of the author of the book or of the document. So it is not very crucial. Okay. Okay. So now let's say that we look at our Fibonacci sequence. So I guess that those in IT, some of you may have already do some small programming exercise to calculate the terms of the Fibonacci sequence, and you may have already known some formula or some algorithm. Okay, but now let's say that we want to calculate f of 100 in a naive way. If we only use the initial conditions and the relations, then we will need to calculate f2, f3, f4, f5, and so on. So it will take a very long time to reach f of 100. So it is not very efficient. So maybe if we have some analytic formula, then we can, if we can write f of n as some function of n, for example, then it may be easier to calculate the terms, the generic term and arbitrary term of the sequence. All right. So in order to find a formula, a general formula for the terms of a sequence defined by a homogeneous linear recurrence relation and some initial conditions, we need mathematics. Okay. So here is two. Okay, so I will give you the general solution later, but it will be later. I prefer to start with an example. Okay. Okay, so let's start with the Fibonacci sequence. We both know that we have fn is equal to fn minus 1 plus fn minus 2. Okay. Okay, so this is not a very pretty example. Let's consider another relation. Let's say we have a sequence A of n, okay, where n is non-negative, defined by the relation A of n is equal to 3a n minus 1 minus 2a n minus 2 with some initial condition, okay, with some a0 equal to some value and a1 equal to some value, okay. So if maybe for some of you who have studied in specialized schools or classes for mathematics, you may have known that the way to to do this is to write it as follows. Okay, you take 2 times a(n minus 1) to the left, and it leaves you with this. So here you see some pattern that will repeat. So you can continue, and it will be equal to. So this is not very good, because okay, I want some coefficient here. So we can write it like this. So you see that is 2 times okay. So if we use an auxiliary sequence, if we set b of n equal to a of n minus a of n minus 1, okay, for n larger, greater or equal to 1, then this will give us bn is equal to 2 times bn minus 1, and we can continue until the smallest term. So it will be equal to 2 to the power n minus 1 b1. Okay, so you have a generic formula here. So if you plug it back, then you will have a of n will be equal to bn plus bn minus 1 plus etc. plus b1. b1 is a1 minus a0, so you need to have one a0 here, and then you can replace this. It will be equal to a0 plus how many b1? So we have b1 here, 2 to the power n minus 1 plus 2 to the power n minus 2 plus etc. plus 1. Okay, and after some rewrite, it will be equal to something of the form a plus b times 2 to the power n, where a, b are some constant that will be that depends on the initial conditions. Okay, so here it is not easy to see, but in fact here there is n here. So in this example, we have a generic term a times 1 to the n plus b times 2 to the n. And what is the particularity of the numbers 1 and 2 here? So if we look at this example, 2 here is present here, and in fact the 1 here is related to a minus 1 times a n minus 1. Okay, so you can see that. So I will erase this. So the key observation here is that you can write in this example so here the key here is that you can write a n minus alpha an minus 1 equal to beta times an minus 1 minus alpha an minus 2. Okay, so if you manage to write it like that, then you can go back and it will become equal to beta to the n minus 1 a1 minus alpha times a0, and you can continue the argument with a little calculation, and in the end, for those who prefer to do the calculation, you can try it at home. But for the general public, it is important. The important thing that you have to remember is that if you manage to write it as this, then the general term of the sequence will be, we have some constant. What we call the constant? Let's say we have to see for the coefficients, so maybe alpha beta, maybe gamma 1 times alpha to the power n plus gamma 2 times beta to the power n. Okay, so here we need alpha to be different from beta for some technical reasons that we will see later. Okay, so but when will you can you write it like this? Okay, so the idea is to find alpha and beta so that the general term of the sequence can be written in this form, where gamma 1 and gamma 2 are some constants which will be determined by the initial condition. Okay. So if you rewrite this will give you an is equal to alpha plus beta an minus 1 minus alpha beta n minus 2, and if you plug it in the original relation, let's say that here we have C1, okay, plus C2, then this will give you alpha plus beta equal to C1 and alpha beta equal to minus C2. Okay, so if you have this system of equation, is it possible to calculate alpha and beta? You know that this will remind you of the quadratic equation. Okay, this is the Viet theorem. Okay, so that means that alpha and beta are solution to the equation x squared minus 1x minus c2 equal to 0. Okay, so if you have a relation of second degree such as this one, then you will solve this equation to find alpha and beta, and then your generic term will be equal to alpha 1. Of course, this is the case where alpha and beta are different. If your equation has two different solutions, then you have this formula, and then you will use the initial condition to replace n with 0 and 1, in order to solve for the exact value of gamma of the constants gamma 1 and gamma 2. Okay, so that was the idea. So if you are not sure how to solve for the general recurrence relation, then just remember this method to solve the second degree homogeneous linear recurrence relation. Okay, so I will give you the general method here. So do not worry, you don't need to remember all these results by heart. If you remember, then it's good. Okay, it's not difficult. Yeah, if you look at it, then there is a very easy way to remember that there is a logic behind all this. But if you don't, then you can always look at the document, because I will allow you to use a document in the exam, so you don't need to remember everything by every formula, every theorem by heart. But here is easier, right? So you have the equivalence. You have an equal to C1 and minus 1 plus etc. plus C and minus, sorry, CK A and minus K. Okay, so you will write this as x to the power K, the characteristic equation, which is its name, of this relation is, you can find by write xk here is equal to C1 x k minus 1 plus etc. plus ck. So here is xk to the power 0, which is 1. Okay, and then you change the sign, you put everything on the left hand side, and you obtain this equation. Okay, so this equation is called the characteristic equation associated to this homogeneous linear recurrence relation. Okay, so in order to solve for the generic formula of the relation, we need to solve this characteristic equation. Okay, so the root of this characteristic equation is called the characteristic root of the corresponding relation. So this relation is the relation number 1. Okay, so in general, if you know the fundamental theorem of algebra, then you know that this equation, this polynomial equation of degree k, if we consider complex numbers, then an equation like this always have k roots. Okay, so in general, if we consider the complex number, then we will have k characteristic roots. Okay, but in the exercises to simplify your life, we will only deal with the relations which have real characteristic roots. Okay, don't worry. But if you like, you will always be able to. You can also use the complex roots. So you can guess that we will seek the solutions of this equation in the form similar. In the previous example, we have two distinct characteristic roots, and we had alpha to the power n plus something beta to the power n. Okay. So here, for example, for the Fibonacci sequence, we will look for a solution of the form Fn equal to gamma 1. So this root 1 plus square root of 5 over 2 to the power n plus gamma 2 1 minus square root of 5 over 2 to the power n. So here, this is a curious formula in the sense that you know that since the Fibonacci sequence have integer coefficients and the initial values are also integers, all the terms of the Fibonacci sequence are integers. Okay, but here you can see that this is rather curious. You see that in this general formula of the Fibonacci sequence, the roots are not integers. They are not only not integers, but they are also irrational. Okay, they are irrational numbers. But if you combine them somehow you will get integer values. So that is some interesting facts that for those who are curious, you can try to prove. So later, when you have the general formula for the Fibonacci sequence, you can try to prove that it will have if you simplify, if you reduce it, you will obtain an integer value. Okay, so that's a challenge for those who are for the curious among you. Okay, so for the Fibonacci sequence, you can see that the characteristic equation is this one: x squared minus x minus 1 equal to 0. And of course, you can find easily, quickly, this relation has two distinct characteristic roots, which are these numbers. So you can look for, if you look for gamma 1 and sorry, here it is gamma 2. You can try it here. So if you plug in the initial condition, then what will you get? You will get, you let n equal to 0 and n equal to 1. If n is equal to 0, then you have gamma 1 plus gamma 2 is equal to f0, which is 0. And if you let n be 1, then you have 1 plus square root of 5 over 2 gamma 1 plus 1 minus square root of 5 over 2 gamma 2. This sum is equal to 1. And you can solve this system of two linear equations to find the values of gamma 1 and gamma 2. And then you plug back into this formula to find the general formula for the general term of the Fibonacci sequence. Okay, so let us look closely to the case of linear reconciliation of degree 2. Okay, so in the case of degree 2, our equation will have this form. And since C2 is different from 0, then you know that this equation will have two non-zero roots. Okay. So of course, in the general case, we always have two complex roots. But suppose that we have two two distinct roots, real roots, R1 and R2, or compressed roots. It doesn't change the result. Then this theorem states that you can look for a general term of the sequence of this form. Okay, and in order to find the coefficients alpha and beta here, you will let n be 0 and 1, or 1 and 2, depending on whether you start your sequence with 0 or with 1. Okay, so if you start your sequence with 0, then you will have alpha plus beta equal to A0 and R1 and R1 alpha plus R2 beta equal to A1. So normally, since if R1 is different from R2, then you know that this system has a unique solution, okay? Because the determinant of this system is 1, 1, R1, R2, okay? So if R1 is different from R2, then this is non-zero, and you know that there is a unique solution. Okay, so let us complete the example of the Fibonacci sequence using these results. Okay. Okay, so for the Fibonacci sequence, as we have already seen, we have two characteristic roots which are different from each other. So we will look for a formula for the general term of this form here. Okay, so these are our R1 and R2 here. Okay. So this will require some calculations. So you need to get out your pen and a piece of paper to do. So it is not very difficult. So you will see that after some quick calculation, you will find alpha equal to 1 over square root of 5 and beta is equal to minus 1 over square root of 5, and which will give you this formula. So as I said, it is interesting that in this formula you have some irrational number involved. You have square root of 5 here. But somehow if you develop some, you can try to develop all these terms using the Newton's binomial formula, and then and after some simplification, you will find that there will only be integer terms remaining. So after that, so this doesn't contradict the fact that the numbers, the Fibonacci, the numbers in the Fibonacci sequence are integer. Okay. Of course, if you are into algorithms, then this formula is good for doing math, but it is not a very practical formula for computers to calculate the terms of the Fibonacci sequence. So, but that is another subject. If you are in the algorithm course, you may encounter some different algorithms to quickly calculate a term for the Fibonacci sequence. Okay, but here now we are doing math, so we are happy with finding this formula, which looks kind of nice. Okay, so it looks it looks kind of symmetric. And you can see that here the exponents of the both terms are n, so they have equal, and they are kind of symmetric. So this is a nice formula for the Fibonacci sequence. Okay, so what happens in the case that we have a double root for the characteristic equation? So let us remind ourselves that here we were able to find alpha and beta because of this the system of equation. Okay. So here, if we keep this formula for the for the case where R1 is equal to R2, then we have a problem here. Then this will become alpha plus beta is 0 and alpha plus beta equal to A1 over R1. Okay, so in general, there is no reason for these two values to be equal to each other. So this formula, this formula for the general term doesn't work for the case where we have a double characteristic root. But in fact, if you continue the approach that I represented, if you continue to write, if you write it as n minus R0 here, and minus 1 equal to R0 and minus 1 minus a and minus 2 and so on. If you do some calculation, then you arrive at something like this. So maybe for the curious boys and girls, you can try to prove this, but for the general audience, we will be happy with accepting this formula. Okay. So so the difference is that there is a coefficient n here. Okay. So previously here we have some a linear combination of R1 to the power n and R2 to the power n. So here we still have R0 to the power n, but we have a nonlinear term here. Nonlinear because we have something that depends on n here. It is not a constant anymore. So as before, you can once you have this formula, when you know what is R0, you can plug it into the initial condition in order to find alpha and beta. So if let's say that our indices start with 0, then you will have alpha. Sorry, alpha equal to 0, and if n is equal to 1, then you have alpha 0 plus beta 0 is equal to A1. And of course, these two equations allow you to completely determine alpha and beta. And of course, here you can see that the alpha is equal to A1. or you can write it explicitly, then beta is equal to A1 over R0 minus A0. Okay, so it's easy. And please note that here we are able to take the division by R0 because what? Because we have, since our relation is of degree 2, this is our equation, right? So because of this, you have R0 square is equal to minus C2. And since it is a relation of degree 2, this must be non-zero. So as a result, R0 here is non-zero. Okay. So the condition that the second coefficient is non-zero is crucial here. So remember that you only use this if your C2 is different from 0. Okay. So as usual, it is better if we apply our results directly to an illustrating example. Okay, so let's look at the equation. So you can see easily that the characteristic equation will have a double root. R0 is equal to 3, right? Because it is this. So we will. So if we if we apply what we have seen, we have alpha equal to A0, which is 1. Beta is equal to, what did we have? We have A1 over 0 minus A0, which will give us, can someone tell me, which is 6 over 3 minus 1, which is 2. Correct? No, it's not 2, sorry. Six divided by 3 is 2. Okay, so then we apply here and we get the general term of this sequence is n equal to 3 to the power n plus n times 3 to the power n. Okay, do you understand? Yeah, you understand this example, right? Okay, so we have treated the two cases for the simplest of our relations. That was the relations of degree 2. For the general case, it is a little bit more complicated, but we also distinguish two cases. The first case is when all the roots, all the characteristic roots are distinct. Okay, so this case is easy. So you might have guessed that we have a similar result if the characteristic equation have k distinct roots. Then the general formula for the general term of the relation is simply this. In other words, it is a linear combination of Ri to the power n, okay, where Ri's are the roots of the characteristic equation. Okay, So if the characteristic equation have different roots, then everything is okay. So it is easy. So in order to determine the coefficients of I, you will have to write the conditions. So you will have if n is equal to 0, you have alpha 1 plus etc. plus alpha k equal to a0. Then you have r1 alpha 1 plus etc. plus rk alpha k is equal to a1 and so on. And for the curious ones among you, I have a challenge for you. That is to prove that such a system of linear equations always have a unique solution. That means that, or in other words, you can prove that if R1, R2, until Rk are distinct, then this matrix has a non-zero determinant. So this should be 1 to the power k minus 1, 2 to the power k minus 2, and here we will have rk to the power, sorry, k minus 1 on all the bottom row here. So you can prove that this determinant is non-zero. So it is a little bit linear algebra here. So a small exercise for you. As a hint, you may, no, I will not give you the solution. So it is up to you to find out. Okay, so this case is easy. And for the general case, it looks a little more complicated, but in fact, not so. There's some logic, there's some rules here. So in this case, it is, of course, more complicated than the case of degree 2, because in degree 2, you only have two cases, okay? You have either R1 and R2 are different from each other, or R1 is equal to R2. But when your characteristic equation has a higher degree, then there may be many cases. For example, if k is equal to 3, then you may have the cases where you have 3 different roots, or you have you have a double root and a single root, or you have a triple root. Okay, so if k is equal to 4 or higher, then you have many more cases. So in the general cases, suppose that your characteristic equation has roots with multiplicities in Vietnamese board. Okay, so here you suppose that this equation has mid board. Okay, so let m1 to mt be the multiplicities of the corresponding roots. Okay, so all the t values are different from each other, and you need that the sum of all the multiplicities is equal to k, of course, because it is a polynomial equation. The total number of roots, if you count the multiplicities, should be k. Okay, then the solution, we have this form here. here each p1 to pt of n is a polynomial, and the degree of this polynomial is at most mi minus 1, where I is the multiplicity. So you can apply to the case of k equal to 2. You have one root r1 and m1 is equal to 2. So according to this, the general formula for the general term is an is equal to p1 of n r1 to the power n, okay? And since the degree of this polynomial p is smaller than or equal to 2 minus 1, which is equal to 1, we have this, we can write this polynomial as, what is it? AB, ABC, what do we use? Alpha n plus beta. And you refine the formula in the previous section for the second case of relation of degree 2. Okay? So this you do not need to know it by heart. The important thing is to remember the degree of each polynomial is determined by the multiplicity of the corresponding root. Of course, we will not do many exercises involving this result, but this result is included here for the sake of completeness. Okay. So let us take a break. Let us take a break, and after the break, we will look at the more complicated case where our recurrence relation is non-homogeneous.
Recording stopped.
Okay, so let us resume.
Recording in progress.
Okay, so we finished this lecture with talking a little bit about the non-homogeneous linear recurrence relation. Okay? So as you have seen, when we talk about non-homogeneous linear recurrence relation, you have something that you have a linear recurrence relation. So the first part is similar to the homogeneous recurrence relation, but you have a non-homogeneous term here, which in general we can say that it may be a constant or maybe a function, but in general we assume that it is a non-zero function in M. Okay. So of course we assume that it is non-zero, because if it is zero, then we find ourselves in the previous case, and we have already treated that case. Okay? And here we also need the condition that the last coefficient ck is different from zero, because it will have us determine the degree of the recurrence relation. Okay. So the idea. So let me ask a question. Have you finished the linear algebra course? Hello.
Yes.
Oh, yes.
Okay. So you have you have already learned about homogeneous and non-homogeneous linear system, right? Have you learned about the solution to linear systems of equations? Hello? Do you understand my question?
We have.
Okay, so here you can see that here we have a similar idea. So in linear algebra, in order to solve a non-homogeneous linear system, you have to you know that the general solution to a non-homogeneous linear system is a linear combination of a particular solution to the non-homogeneous system and a generic solution to the associated homogeneous system. Okay, so here you have the same situation. We, in order to solve a non-homogeneous linear relation, we will first have to solve the associated homogeneous linear recurrence relation. Okay, so the idea is that you can find the parallel between this and the solution of a linear system. Okay, so here the idea is that if you know a particular solution to this non-homogeneous relation 3, okay, then any combination of this particular solution and a solution to the homogeneous, here H is for homogeneous, okay, so here you have a particular solution to the non-homogeneous case, and you have a generic solution to the homogeneous case. And then this theorem say that the generic solution to the non-homogeneous case is the sum of a particular solution to the non-homogeneous case and a general solution to the homogeneous case. And this is this holds in the two sense. That means that this is a solution to the relation 3, and conversely, any solution to this relation can be written under this form. So, so if you have a particular solution to the non-homogeneous relation, then theoretically you know all the solution to this relation. All right. So it's very similar to the linear system, and further in later year in later courses, if you study differential equations, then you will re-encounter this idea between how to use the associated homogeneous case to find the general solution to the non-homogeneous case. Okay, so to illustrate, let us look at an example here. So in this example, we don't talk about how to find. So this theorem is not very useful because it says that if you have a particular solution, okay, so it hasn't told you yet how to find such a particular solution, but we will look at it later. But now, let's say that, suppose that we have a particular solution to our non-homogeneous relation. Then, in this example, we have this relation. So, for simplicity, we look at a relation of degree 1. Okay. So here we have k equal to 1. The associated homogeneous relation is this simple relation an equal to 3a n minus 1, and your function fn is this function, is this linear function fn is equal to 2n. Okay, so you can easily see that a general solution to the associated homogeneous relation is an is equal to 3 to the power n of 0. Okay, so so as written here, you have this homogeneous solution. Okay, so here alpha is a constant, which is in fact equal to a0 over 3 or a1 over 3. Okay, so now now let us cheat a little bit. Okay, so we don't know how to find such a particular solution, but now suppose that we know a particular solution, which is given here. You can verify this is a particular solution. If you don't believe me, then you can plug it into this. You can verify minus n minus 3 halves is equal to 3 times minus n minus 1 minus 3 halves. Okay, plus what do we have here? 2n. So we will have the, is it the same? I think. So you can verify that this satisfies this relation. So here you have, if you take n, you have minus 3n plus 3n. So you have minus 3n plus 3n plus 3 times inside you have 1 minus 3 halves. So it's true. It's true. So this is a particular solution to this relation. So according to the previous theorem, a generic solution to this relation would be, so we will have something like an is equal to this particular solution minus n minus 3 halves plus alpha times 3 to the power n. Okay, and now in order to determine the exact value of alpha, we will use the initial condition. So we replace n with 1 here, and we will have minus 1 minus 3 halves plus 3 alpha is equal to a1, which is 3. And from this, can you help me to calculate alpha? What is alpha? We have this. So what do you find? What is alpha here? Alpha should be equal to something like, so it's 3 plus 1, which makes 4. 4 plus 3 halves will be 4 plus 3 halves over 3, which is equal to 11 over 6. Okay, so our calculation is correct. So the general term for the solution for this equation with this initial condition is n is equal to minus n minus 3 halves plus 11 over 6 times 3 to the power n. So this is the solution. So you can verify. You can use, if a1 is equal to 3, then what is a2? a2 will be equal to 3 times 3 plus 4, which is 13. You can plug n equal to here to see it is equal to 13. We have minus 2 minus 3 halves plus 11 over 6 times 9, which is minus 2 minus 3 halves plus now 53 over 2. Is that, so that makes 30 divided by 2, that makes 15. 15 minus 2, so it is correct. Okay, so you can see so this, so it works in this example. So you can see that it applies to this example, gives us the correct formula. So if you don't believe yet, if you still don't believe, then you can try, you can continue to verify with n equal to 3 or 4 and so on. Okay. So now if someone gives us this particular solution, then it will become easy for us. But now the question is that how do we find this one? It looks kind of random. Okay, so I will talk about it. So I haven't talked about it yet. So that is the purpose of the next part. Okay, this is this theorem. Of course, in general, we don't know how to find an exact and analytic solution, but for some function fn which are reasonably nice, then we know we have some method to find a particular solution. So yeah, so what does it mean that fn is reasonably nice? So here is one case. So this theorem states that if fn is some polynomial, and we can add times some exponents, times an exponential function in n, then we know we have a method to find a particular solution for the relation. Of course, we are always talking about we always talk about a relation of this form. Okay. So now suppose that we have a relation like this, and in which fn has this form. So in many exercises, in many cases that you will work with, fn is indeed a polynomial, but in case fn is a polynomial, do not forget that if fn is a polynomial, that means that s is equal to 1. Okay. Now there are two cases that you have to read the description of the two cases and apply. You will understand better with practice, and I will demonstrate by an example. But since you will have access to documents, you don't need to learn this by heart. You only need to work out some examples once or twice to get a feeling how it works. And then after you have seen how it works, then you do a couple of exercises on this, and then you move on. You can forget the detailed formula, but it is important that you can you may forget the formula, but you need to remember the general idea that if fn is a polynomial in n. Okay, so here remember that the variable here is n. So if fn has this form, then you can look for a particular solution of this form here, where p a polynomial, and this polynomial has a degree not smaller than or equal to the degree of this polynomial bq. And in the second case, we distinguish two cases. Okay, so if s is the root, is not a root, then you have this form. If s is the root of multiplicity m, then you have a factor in front of this form. So here, let's look at this theorem in action. Now, you know this sequence, right? So you all know that the formula for the general term of this sequence, you know that it is n times n plus 1 divided by 2. Okay, but now we will try to to find this formula, not by the method that you are used to, but now let us look at this under the view of linear recurrence relation. Okay, so if we have a sequence like this, then you can express this this sequence using this recurrence relation and an initial condition. So here, do you agree that if you write it like this, then you have this sequence satisfies this relation, right? So a n is equal to a n minus 1 plus n. Okay. So now you first we solve the associated homogeneous relation. So the homogeneous case, homogeneous solution, you have a n h. This is simple. It's a constant, right? It doesn't change. Now now we need to look for a particular solution. So here, our f of n is equal to n times 1 to the power n. Okay, so here our polynomial q of n is equal to n, and s is equal to 1. Okay, so now is 1 a root of, sorry, there is no n here. Is 1 a root of this polynomial? Now, right? This the root of this polynomial is 0. So s is not a root of this polynomial. So let us look at the theorem. So s is not a root of the the homogeneous. S is the root of this. The characteristic equation is x minus 1 equal to 0. So s is the root of this equation. Okay. So we find ourselves in the second case. So s is the root of multiplicity m. So it is a single root. So m is equal to 1. So we will look for a particular solution of the form n to the power 1, n to the power 1. And since small n is a polynomial of degree not exceeding the degree of this, so you will have, here we have alpha, so we have beta n plus gamma times s to the power n. Okay, so we will need to find AP of n of this form, or beta n squared plus gamma n. Okay. Now, in order to determine beta and alpha and gamma, we plug it into this relation, and we have beta n squared plus gamma n is equal to beta n minus 1 squared plus gamma minus 1 plus n. Okay, so this is This is an, this is an minus 1. We plug it into this relation, and we will obtain beta n square plus gamma n equal to beta n square plus, we will group the terms of n. So we have minus 2 beta here plus gamma plus 1 n, and the free coefficient is plus beta here minus gamma. Okay. So since this verifies for all n, it means that the corresponding coefficient of the two sides must be the same. So we need the coefficients of n squared should be the same. So beta is equal to beta, it is automatic. The coefficient of n should be the same. So we have gamma on this side is equal to minus 2 beta plus gamma plus 1, and the free coefficient 0 is equal to beta minus gamma. Okay, so you solve this and you obtain beta equal to gamma equal to, from this equation you have beta equal to gamma, and from this if we replace gamma with beta, then we get 1/2. Okay, so we plug it up here and we have 1/2 n squared plus 1/2 n. Okay, so do you follow, do you understand the method? First we have to determine what is q. Okay, here q is n to the power 1, s is equal to 1. Okay, the characteristic equation of the associated homogeneous equation is this one, x minus 1 is equal to 0. So s is the solution to this equation with multiplicity 1. So we find ourselves in the second case. So according to the previous theorem, you can look at the theorem. Our particular solution must have this form here. So we write our particular solution to this form. We plug this into the recurrence relation, okay? And then we identify the coefficients of n squared, of n, and the free coefficients of the two sides in order to obtain this system of equations. Okay? We have this system of equations, and then from this system of equations, we solve to obtain beta and gamma equal to 1/2. And then we plug in this, we find this particular solution here. Okay? So AH is constant, AP is this. So our general solution, can I erase the bottom part here? So I erase this. Okay. So now our general solution will be 1/2 of n squared plus 1/2 of n plus alpha. Okay, So we have n is equal to this. And the final step is to plug this into the initial condition. So we have 1/2 of 1 squared plus 1/2 times 1 plus alpha equal to 1. Okay, so alpha is 0. Then we plug back to here, and we find the familiar formula for the sequence. Okay, and now you can apply this method to find similar formulas for similar sequences. So okay, so here it is written here. So here m is equal to 1. Single roots, single mean multiplicity 1. Okay. So we look for this, and you obtain P0 P1 equal to 1/2, and you obtain this. Okay, and similarly you can apply. If you are curious, you can try with the sum of squares or the sum of cubes of the first n integers and so on. Okay, so that was for today. Do we have any question? Okay, so there are not many results, but the important is that you do some exercises for each of these results. Do some of the exercises to get a feeling about the idea. Okay, you need not remember the exact formulas, but you need to get the idea how it works. Okay, you can look at but the important things is that you get the idea, and then you need to do some exercises in detail until the final result. And then it is a good habit to check the result by plug it into the relation to see if it verifies the relation and the initial conditions. Okay. So do you have any questions?
No, sir.
Okay, so if you have no other question, then we can stop today's lecture here. And next time we will talk about an advanced method to solve counting problems and to solve recurrence relations. Okay. So goodbye, and hopefully we can see each other in person next week. Okay. Bye bye.
Hope so.
Bye,
Bye,
Professor.
Bye, Professor.
See you next week.
Recording stopped.
Bye-bye.
Goodbye.
Bye.